Okay, so we're going to look at concavity. So let's just look at a function. Let's think about a parabola. Here we have a function that is concave up. And that makes sense that it's concave up. It opens upward, it's concave up. If we think about the slopes of this function, or if I want to draw the graphs of the tangent lines to this function, they're going to lie below the function. And it's hard to draw on this little thing, so bear with me. I can't get it right on there. But notice all these little tangent lines lie below the graph. And notice, too, that the slopes are going from negative values, getting closer to 0, and then they're going to positive values. So here we could say that on this graph, f prime is increasing. So when f prime is increasing, going from negative to 0 to positive, we have a graph of a function that's concave up. If f prime is increasing, what do you think that says about the second derivative? Is it positive or negative?
Positive.
It's positive. Okay, because the second derivative is the slope of the original function. Of the derivative. Second derivative is the slope of the derivative. So if the derivative is increasing, then the second derivative is positive. All right, and notice too that the tangent lines lie below the graph. And this is a function that is concave up. Now let's look at a function that's concave down. This is a graph of a function that's concave down. If we think about the derivatives here, again, this time the tangent lines lie above the graph. And they're going from extremely positive to less positive to 0 to negative. So here we would say that f prime is decreasing. Because it's going from very, very steep, which means very high, to smaller numbers, to 0, and then it begins to go to a negative slope. And the tangent line lies above the graph.
If it's always facing down, is it always going to be decreasing? Like if the concave's always down?
Mm-hmm. F prime is decreasing. So what does that tell you? What do you think might that mean about the second derivative? It's going to be negative if we're concave down. This is concave down. If you want to write out down, you can, but I understand what you mean if you have an arrow pointing down. So let's just think about a simple function that we know what it looks like, y equals x squared. Y prime is 2x, and y double prime is 2. So would you expect that to be concave up or concave down? Concave up. We know what that graph looks like. It's similar to what we just looked at. So if you have trouble remembering which is up and which is down, always go back to y equals x squared. Because you can easily find the second derivative of y equals x squared. You know what it looks like, and so that helps you remember. If you have a positive second derivative, you're concave up. If you have a negative second derivative, well, we know that y equals negative x squared. It's like this. You learned that way back in Algebra 2, maybe Algebra 1. I think Algebra 1. Those were the days. All right, but look how intelligent you are now. So here our second derivative would be negative 2, so we know that if it's a negative second derivative, we're concave down. So when we're checking for concavity, that gives us a little more detail if we are going to draw the graph. But we do it very similarly to using the first derivative test. We find where the second derivative is 0 to set up our test intervals. And we do test intervals based on the second derivative. All right, here's my function. And I want to determine the intervals on which this function is concave up or concave down. So to get to the second derivative, we have to go through the first derivative. Before we do that, are there any restrictions on the domain? No restrictions on the domain. The domain is negative infinity to positive infinity. So that won't affect our intervals. We need to check that because if there are restrictions on the domain, it can affect our intervals. Okay, there's nothing that we can square that when we add it to 12 would give us a 0. Because we are only dealing in real numbers in calculus. No imaginaries. I know. Yes.
I was like, why did we learn that? And how
Because if you're trying to find roots for functions that don't cross the x-axis, there may be some theory classes that still use complex. Those were not my favorite in college. All right, so we're going to take the derivative. Denominator times, well, actually, if you wanted to, we could write this as 24 times x squared plus 12 to the negative 1. We can do the quotient rule, which is harder, but that's okay. What's the derivative of 24?
0.
Minus the numerator times the derivative of the denominator over the denominator squared.
That's not that bad.
All right, so this gives us negative 48x over x squared plus 12. So if I were looking for a critical number, what would it be?
Or do we set it equal to 0? Oh.
X equals 0. And when you have a fraction, all you have to worry about for the setting it equal to 0 is the numerator. Right? It's possible that something could have emerged that gives you 0 in the denominator, but that's not where the function equals, that's not where the derivative is 0, that's where it does not exist. But that's still a critical number. Yes, ma'am?
Okay, are critical numbers kind of like asymptotes in the sense that you have to have x equals this?
Yeah, I would put it that way.
Okay.
I don't know that they would count it wrong, but it's a good idea, whatever your variable is. All right, so let's go to the second derivative. Since it's not an equation, it probably wouldn't be that important. No. Okay, we've already determined that there's nothing in the denominator that could give us 0. And even if there were, we would have already excluded it from the domain, so it wouldn't be a critical number. All right, so this time we have to use the quotient rule. So we have the denominator times the derivative of the numerator minus the numerator. Don't forget that you're subtracting there. Times the derivative of the denominator. Ladies.
She said we had to use it on this part. So wait, why wouldn't we have to use it on the first part?
Because you could have rewritten that as 24 times x squared plus 12 to the negative 1.
I was really confused.
All right. Shh. Grace, did you have a question?
Yeah, is that chain rule at the end?
Yes.
Okay.
at the end of it, and just like do X.
That's the end.
I mean, just 2X.
Oh.
All right.
And that's the-
Notice, I have two separate terms in the numerator. And in both of those terms, I have a 48 and an x squared minus 12. So I'm going to factor that out. Or x squared plus 12. And here I'm left with a negative x squared plus 12 plus 4x squared. All over
2X.
x squared plus 12 to the fourth power. All right. This cancels with one of those, and I'm left with 3.
Whoa, what's going on?
And we have 48 times negative x squared plus 4x squared is 3x squared minus 12 over x squared plus 12 cubed.
Why is it?
Because we have to distribute that minus. Right. Now, the places where we need to check our intervals. So I'm going to see where is the second derivative equal to 0. Okay, to figure out where the second derivative equals 0, or does not exist, but there's no cases where it doesn't exist, we set the numerator equal to 0 and solve. So I don't have to worry about the 48. That's going to divide out. 3x squared minus 12 equals 0. 3x squared equals 12. X squared equals 4. So x equals plus or minus 2.
So wait, why did you set the second derivative to 0? It says-
That's where we're checking concavity.
Okay.
First derivative checks increasing and decreasing. Second derivative checks concavity. Whether we're concave up or concave down. Michael,
On the second derivative, did you have to use quotient rule, or could you
I-
do it the other way?
You can do
I
it
had
the other
used for the going from the original to the first. I could have done it the other way. Second derivative quotient rule.
Okay.
way.
All right. So now we've got intervals to check.
Can't put this, put x squared plus 12 to the negative 3 on top.
If you wanted to, you could factor out a 3 here, which might make it a little bit easier. Oh, it's 144? Is that what you said it was? Okay. When we plug in, that might make it easier. X squared minus 4.
How did you take out 1.4?
Well, we factored out a 3 and multiplied it by 48.
Oh, okay.
So I'm going to check from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. And we plug a value into the second derivative. I don't care what the value is. Is it negative or is it positive? Jen?
So is it plus minus 2 also a critical number?
They are not critical numbers. These are possible points of inflection, and that's where concavity changes. Possible points of inflection.
So where would that look like on a graph? So it'd be
Up.
where it would be going from.
From concave up to concave
Or, like,
down.
What is the point of that spot? Like just in the middle of the two
Yes.
max and min?
Well,
Like, if it was like
sometimes.
this, it would just be like in the middle.
If you had, it's probably right about there.
So
It's
like
where the
that-
second derivative equals 0.
What did I say? 5 times of what?
All right, so second derivative, if I plug in, let's say, a negative 3, we're going to have 9 minus 4.
What's inflection?
It's where concavity changes.
And you plug it into the second
Second derivative. So 9 minus 4 is positive.
Where's the dang it.
This is my second derivative simplified.
Oh, I couldn't see the 4 of those.
Okay, if I plug in a 2, I'm going to get less than 0. And if I plug in a 3, I'm going to get greater than 0. So on the interval from negative infinity to negative 2, we are concave up. From negative 2 to 2, we are concave down. And from 2 to infinity, we are concave up. So that means I do have a point of inflection. I have 2 points of inflection. It's where concavity changes.
So finding points of inflection is like finding maximum.
Yes, it is. We go back to the original. So if I want to find my point of inflection, I'm going to plug a negative 2 into the original and a 2 into the original, which is 24 over 16, which is 4 goes into both of those. 3 halves. And if I plug in a positive 2, we get 3 halves.
So you plug in the original.
Plug it back into the original function. All right? One thing I'll mention about points of inflection, if concavity doesn't change at the possible point of inflection, then you don't have a point of inflection. Concavity has to change for it to be a point of inflection.
So like that one where it kind of went up and then up more.
If it keeps going up, then, well, that would, concavity changes. But if you had a 4th degree that looks like that, concavity doesn't change. We'll look at one in a minute. Okay, let's look at this problem. Shh. Anything that we have to exclude from our domain?
3 and negative 3.
Okay, x cannot be plus or minus 3. So that means we're going to have to consider that when we consider our intervals.
Oh, is it going to have a asymptote?
There's probably going to, well, yes, there will be asymptotes at plus or minus 3. Because there are no common factors that factor out that would just give us a whole. All right, so we got to take our first derivative. So denominator times the derivative of the numerator. Anna. Minus the numerator times the derivative of the denominator over the denominator squared. Here you can just multiply everything out if you want to. 2x cubed minus 18x. Rather than factoring out a common factor, that's not that helpful. Minus 2x cubed minus 4x over x squared minus 9 squared. So this really works out pretty easy. And we get negative 22x over x squared minus 9 squared. If I wanted a critical number, it would be x equals 0. So if you need to get a critical number here, x equals 0. Sir? Would it also be plus or minus 3?
No.
Why not, Emily?
I think that's like doesn't exist there or something.
It's not in the domain. Plus or minus 3 are not in the domain, so they're not critical numbers. All right. We said the domain here, x squared minus 9, we have to exclude. All right, so let's find the second derivative. Well, but we have to.
She does.
Quit whispering. Okay. Denominator times the derivative of the numerator minus the numerator. I'm going to just do that. No, it's just 2.
Wait, why'd you put plus?
Because it was minus a negative.
It's going off the screen.
Still, I moved it some.
I mean, it's just an X.
Is it 2x?
Notice, I have common to both 22 x squared minus 9. And that leaves me with a negative x squared minus 9 plus, this had left, that left, 4x squared.
So we never go back to the first derivative, right? Always just, the reason we have to find the first derivative is to find.
To get to the second derivative.
But we never put
Now, later we will. When we actually begin graphing the functions, we'll need both.
Okay. Good job. I'm gonna do it anyway.
Yeah, I mean, you've got to go through the first derivative to get to the second.
Yeah.
Okay, so that cancels. Let's see what we can do to simplify. This one's going to come out a lot like that last one. Negative x squared plus 4x squared is 3x squared plus 9.
One bracket, one parenthesis.
One parentheses.
It doesn't know if it's closed or open. Does it matter which one you use?
No, it wouldn't matter.
It thinks it's a closed, but it's.
All right. Do we have anything that would make the second derivative equal to 0?
Yeah.
What? We're only worried about the numerator right now. Anything that would make that numerator equal to 0. Whoops. Well, let's see. 3x squared plus 9 equals 0. 3x squared equals negative 9. No.
No.
So all we have to do is worry about our intervals that we established with our domain. Negative infinity to negative 3, negative 3 to 3, and 3 to infinity. Okay. So second derivative, if I chose a negative 4, well, the denominator's going to be positive. 16 minus 9 is positive. And the numerator's always positive. So all I have to really check here is the denominator. Numerator will always be positive. So this is positive. If I choose a 0 in the denominator, I get a negative. And if I choose a 4, it goes positive again. So here we're concave up, concave down, concave up.
How would you get a negative if you plugged in 0? Into that 22, 3x squared?
In the denominator. Numerator's always positive. So
Right.
all I'm looking at is the denominator.
Is it positive 22
Yes.
times 3x squared plus 9?
That's the numerator.
If you plug in 0, would it just be 9 times 22?
Yeah. But what happens on the bottom?
Oh, I thought you said that it didn't matter.
No, we do have to look at the bottom here.
Oh, okay.
We don't really have to look at the numerator. Okay, so if we were going to think about this graph, you already told me that at negative 3 and positive 3, we're probably going to have asymptotes. Now, we could get more detailed information, but if we're concave up over here, it's probably going to look something like this. Concave down, concave up. Placement is, my placement may be off, but as far as concavity is concerned, that's what it would look like. No points of inflection, because there's no point on the graph that you can pinpoint where concavity changes.
And the points of inflection,
There are none.
because
There
there
was
is no
n-
critical number.
Well, we don't really call them critical numbers for the second derivative. It's possible points of inflection.
Okay, but
No poi.
you find it the same way.
You find it the same way you find critical numbers. Yes, sir. All right, if we have f of x equals x to the 4th. First derivative is 4x cubed. Second derivative is, what are my possible points of inflection? 0. So we're going to check from negative infinity to 0 and 0 to infinity. Okay. You can get the assignment off Ringweb, Alice. Okay. If we check the second derivative, positive or negative? Positive, first derivative. Second derivative in this interval. Positive. So there's no points of inflection. It's always concave up.
Why?
Because the second derivative is always positive. Yes, ma'am. All right. Questions on second derivative? All right. Your assignment is on page, can't read, see through Matt's head. Page 189, move. 13, 17, 21.
Yeah, 'cause you don't have to have a brain.
Okay.